thanks everyone for joining. My name is Steffen Smolka. I work in the network infrastructure group at Google. That's the team that builds all the software that we use to drive our data centers, both for Google and Alphabet. So services like YouTube, Google Search, all of Google Cloud run in the data centers that we develop the software for. Today I'm extremely excited to tell you about the work of a small team within that group called the P4-Based Automated Reasoning Group. That's a team I lead at Google. And so P4-Based Automated Reasoning is an approach that allows us to roll out and develop new network functionality quicker into our network, but without sacrificing network reliability. And in fact, we increase network reliability. So let me tell you how we do that. So many of you will know the P4 programming language. The idea is that you write a program where you can specify in great detail how a network switch will process packets in the data plane. And you can then run and execute such P4 programs on specialized programmable network ASICs that were designed with P4 in mind. So that's how P4 was originally intended. However, at Google and increasingly in other places, P4 is used almost in the opposite way. So we still have a lot of fixed function ASICs in our networks. And so these ASICs cannot support P4. So what we do instead is we write a program that matches the behavior of those existing fixed function ASICs. So we use P4 as a modeling language rather than a programming language. Now, it's not immediately obvious why you would do such a thing. But the answer to that is P4-based automated reasoning. That's what this talk is all about. So bear with me for a moment. We'll get there. But first, let's go back in time for a couple of years, around 5 years, when software engineers at Google started thinking about what our next generation software-defined networking switch for the data center should look like. And we had a couple of design goals in mind. So one was, obviously, we should build this based on the newest, fastest available hardware, new ASICs, new optics, et cetera. But also, we wanted our switch stack to be open source and industry aligned, so it would be easier for us to collaborate with external partners. Moreover, we wanted the switch stack to be silicon independent, so we could integrate all kinds of ASICs from different vendors, fixed function ASICs, programmable ASICs, and so on. And also, we wanted to migrate to a newer generation of SDN APIs from OpenFlow to P4 runtime to take advantage of these capabilities of the new generations of ASICs. And we had to integrate this new switch stack into our existing SDN controller called Orion. You may be familiar with it. We have published some papers about that. And then finally, to deliver value to the company, as part of this project, we actually had to deliver a new data center design using these switches. Okay, and so when we started looking at the timeline for this project, it turned out this is kind of a very ambitious project because we kind of need to make changes across the stack. And ideally, you would build it in this sequential way, right? One thing after another, but obviously we don't have time for that, right? And so what you end up doing is this, where you kind of build and design all the things all at once. This is very challenging. It means you don't really know the final requirements of the layer above you when you start building things. And similarly, you don't really know the final specifications of the layers below you when you start building things. And so you want to do all of this, and at the end of the day, what comes out needs to be more reliable, at least as reliable, but probably more reliable than the existing infrastructure. That is very, very challenging, right? So we were basically trying to figure out how to pull this off. And the key trade-off that you run into is this trade-off between feature velocity and reliability. So on the one hand, we kind of know how to build very reliable systems. The idea is, once you have an idea of how the system is supposed to behave, you could write many, many, many tests. And sure enough, you get a very reliable system. But of course, it takes a lot of time to do that, right? It's very costly to do that. And moreover, once you have those tests, they actually start working against you, because now it becomes really hard to evolve your system, right? You might not get it right the first time. So you then change your system. You need to update all your tests. That takes more time. On the other hand, the other end of the extreme, you can not bother testing at all. and then surely enough, you can move really fast, but also your system is not going to be reliable. And so, right, in practice, obviously, we do neither of these things. We kind of choose some point in the middle. But the key issue is that manual testing really only lets you trade off between these two extreme points. And for this kind of project, we really needed to be in this top right corner of the design space, and it was not clear how to get there. One thing you might do is hire more engineers, but you can only parallelize things so much. You quickly hit diminishing returns there, and obviously also costs a lot of money to do this. So what we kind of needed was this magical thing, which is a comprehensive set of tests should just magically appear whenever we design some new feature or modified an existing feature. So this sounds crazy to begin with, but it turns out that we can actually kind of pull that off. And that's what P4-based automated reasoning is all about. So here's how we do that. So the idea is, can we somehow use automated testing instead of manual testing? And so if you look at our switch stack, it is a very complex system. At the bottom, you have two pieces of hardware, a networking ASIC, a CPU. You run a whole Linux operating system on top of that. Then you have several layers of drivers to abstract the hardware, to abstract the vendor. And then we have the Sonic switch operating system on top of that. That's a 3-layered system. And at the very top, we have a RPC server. That's how our SDN controller communicates with the switch. So there's a lot of complexity here, millions of lines of code if you sum it all up with the Linux operating system. And it's really not obvious how you would automatically test such a complex system. So here's the key insight number 1. So from an SDN controller perspective, much of this complexity really doesn't matter. So if you focus on forwarding, the main two things that the SDN controller cares about is, number 1, how does this switch forward packets in the data plane? Number 2, how can I, the SDN controller, manipulate how the switch forwards packets in the data plane? That's the control plane API. So from that perspective, we really only care about these two aspects. And conveniently, there's already a programming language that can describe exactly these two aspects very precisely, unambiguously, in a machine-readable way, and in a pretty compact way. So what we do is we write a P4 program that captures this precisely, and that takes us around 1,000 lines of code. So that's a dramatic reduction in complexity. And at this point, automatic testing is actually something that's technically feasible. In fact, so P4 is actually, first of all, like I said, this is a small program. P4 is a very restricted programming language. It's not like C++. You have absolutely no recursion in P4. There's no loops. It's really just very simple straight line code. And so you can apply a lot of technology to it that wouldn't work for a general purpose programming language. And so, in fact, there's been a lot of research in this area, a lot of tools that people built, P4 TestGen, ATPG, Mesa, and we built some of our own tools. And so you can automatically generate tests. And the final piece of the puzzle is that once you have an automated test for your P4 program, you also have a test for your switch. Because what you can do is you can run the same test on a simulation of the P4 program, and you can run that test on the real switch, and you can make sure that the two devices behave the same way. So this is called differential testing. And so if you put that all together, you get sort of automated differential testing. This is the key idea behind P4-based automated reasoning. And so we built a whole suite of tools that follow this approach at a high level. So they automatically validate that a given switch conforms to a given P4 specification. So the tools that we've built, one is called the P4 fuzzer. That is a fuzzing-based tool that focuses on the control plane API. It generates valid and invalid API requests and makes sure that our switch behaves in a standard compliant way. Recall that the control plane API is P4 runtime here. And for the data plane, we have P4 symbolic, which generates our test packets, and a P4 simulator called BMV2. That's an open source tool that was developed by others outside of Google. Key idea is that the P4 program is the formal specification that we're going to test our switch again. So I should say that there's really a lot of work in this area, not just the work at Google, but I want to do a quick deep dive to tell you how this works for the data plane. So let's get a little bit into technical details here. So here's the high-level idea. So we start from the switch under test, and the first thing we do is we read all the table entries on that switch, and also we look at the P4 specification for this particular switch that we want to test. And then we install this P4 specification on a P4 simulator together with the table entries. So now we have two devices that in theory should behave the same if there are no bugs. So how do we check that? The basic idea is simple. You send input packets to both the simulator and the real switch. You collect the outputs, and you make sure that they match. The hard part here is that which input packets should we use, right? So ideally, we check for all input packets, but there's more input packets. Even if you just restrict to packet header fields, there will be more packets than particles in the universe. So it's a very, very large number of packets you would have to test here. So we can't do that. We need to be a little smarter than that. And that's where all the magic comes in. So that's where P4 Symbolic comes in, which is our packet synthesis tool. And the high-level idea is that we give this tool some notion of coverage that we want to achieve, like entry coverage. Maybe we want to cover all the table entries on the switches. Maybe some other notion of coverage could be something like packet fade coverage. We want to have test packets that get forwarded and others that get dropped, and so on. And then this tool somehow magically spits out all these test packets to cover all the table entries that we have on the switch. So how does it do that? We use a standard technique from formal methods called symbolic execution. Let me briefly explain it. In normal execution, you start from a specific input to a program, and you sort of go through your program, right, and you take a very specific path through your program. So that's normal program execution. In symbolic execution, the idea is let's replace this specific input with a symbolic input, which is much like a variable in algebra. And now, instead of exploring just one path through the program, we're going to somehow explore all the paths through the program. And whenever the program branches, when there's two possible paths, we kind of collect the constraint that would make us go one way or the other. Okay? So we're just going to collect all these constraints. And now, if you want to generate an input that hits a particular place in the program, what you do is you collect all the various constraints on that path from the start of the program to that point in the program that you want to hit. Okay? And then you can take these constraints and give them to a constraint solver. Okay? And there's plenty of off-the-shelf SMT solvers available, like Z3. We use Z3 as a tool from Microsoft Research. And that will spit out an input that satisfies those constraints and therefore takes this particular path through the program. So how do we apply this to P4? You can think of the execution of a P4 program with a bunch of table entries as just an execution of a program. The input to the program is your packet, and your table entries, well, a table is kind of like a big if-then-else statements. If the first table entry matches, execute the first table entry. If the second table entry matches, execute the second table entry, and so on. So the switch basically executes a program. And now we just apply symbolic execution as before. The packet is a symbolic packet. We collect all the various constraints. And our goal might be to hit a very particular table entry, so we get test coverage for that. And then, again, we hand the constraints to the solver, and we get our input packet as a solution. So that's how that works under the hood. Now, that's how it works. Does it actually work well in practice? So we have used this tool for about 4 years now. I have some numbers for the first 2 years. And the answer is it works very, very well. We have found a lot of bugs in the switch stack. In just 18 months, we found over 100 bugs. By now, we've found a lot more than that, in fact. And this is a very conservative approximation where we're excluding all the bugs that were found before the new code was even committed to the code base. So some developers run our tools even before committing code, just to make sure. And so those bugs would not be included here. The next question you might ask is, where do we find bugs? And the answer is pretty much through all layers of the switch stack. Because we use P4 as a reference, sometimes we also have bugs in the P4 specification itself or the P4 simulator, and that's about 10% of the bugs. But a key point here is that this doesn't really hurt us too much. We think it's highly, highly unlikely that we would make the exact same bug in both our specification and in the real switch and thereby miss a bug. Think of this as two sort of low probability events that are independent coming together. The probability of that is very low. If you want to learn more about the kind of bugs we have, we actually had a paper at SIGCOMM 2 years ago. It's called SwitchRe. You can go there and read more on the kind of bugs we find. And finally, how does this compare to, or how many bugs did we miss? There were only 4 bugs for this program in the forwarding plane that then were later found by traditional testing methods, where basically, you build a big data center fabric and do sort of traditional testing. And all of these are actually explained by the fact that we're building all of these, this technology while we were building the switch stack. And so there were naturally still some gaps in our P4-based automated reasoning tools. They have been closed by now. So overall, that's very effective. OK, so a few closing thoughts. So what you've seen here is a sort of a merging paradigm called P4 programs as a formal specification. Google was sort of the first to pioneer this idea, but it's starting to be used by others. For example, Microsoft is using it for a NIC project. And we're seeing people in academia pick up this idea as well. We're working with some partners at Cornell, NYU. And the key contribution of this approach is that it resolves this tension between velocity and reliability. Right? By deriving tests automatically from a specification, you can get really comprehensive coverage of your switch. But you don't get locked into that specific behavior. You can still effortlessly evolve your switch because tests will just get regenerated quickly. You don't need to update them by hand. A few more thoughts before I close. Today, I talked only about finding bugs, but I think that this approach is actually a lot more powerful than just finding bugs. There's a lot more things that we can do based on this. So one thing that vendors really like about this is that we can give them a very, very precise set of requirements for how the switch should behave. And so we can give them the P4 program and all our tools to check that those requirements are met, and then they can go build the switch for us, and they can come back when this is the case, right? So this really helps the vendors. Also, it really helps the SDN controller. The people running the SDN controller at Google, they're happy because they have this formal contract, basically, the P4 program, that tells them exactly how the switch behaves. And they can run a simulation of it, and they'll exactly be able to see what they will get in production. Also, that means that we can easily integrate multiple vendors in our data center because there should be no observable differences between them, and similarly different models of the same vendor potentially. Another thing we can do is we can simulate at least the forwarding behavior of our switches or the entire network based on this model. And you can also apply more advanced technologies like network verification based on this P4 models. And a lot other things you can do. So with that, thank you so much, and looking forward to any questions you might have. Yep.
Does it find the layer in the pin switch that the bug is in, or do you just get like notice like here's a bug, now you gotta hunt down where it is?
Yeah, quickly to repeat the question for the recording. The question was, do our tools tell you which layer of the switch the bug we found was in, or does it just give sort of a high-level bug report? No, unfortunately, we do not tell you where the bug is. We just sort of say that, oh, from a black box perspective, there seems to be some discrepancy between what we expected and what we got. And then we give you sort of details, like why did we expect this particular behavior? For example, for the data plane test, we would say, we send this input packet. This is the output packet we expected. This is the output packet we got. Here's the diff between those two packets. And here's why we expected this output packet. We expected this table entry to be hit. We expected then this other table entry to be hit, and so on. So we can give a lot of details of why we expect what we expected. But we don't at all help you today, unfortunately, with saying where that bug is located in the switch stack. So that would be cool to explore in the future. But today it's all manual. Yeah?
So where do you use the symbolic calculation? Were they using for the input packet and output packet prediction, or you're using something else?
Great question. Let me go a little bit back to this picture. So we use it on the very left to basically figure out what are good input packets to test the switch on, right? Because you cannot just try every packet. There's too many. And if you just did this somehow uniformly at random, you would not get good coverage. So instead, what we do is we look at the P4 program, and we say, well, if we cover all the paths to the P4 program, that should provide us good coverage. But then the problem becomes, how can you, given a path through the program, how do you figure out an input packet that takes that path? And for that question, we use symbolic execution.
So basically, you are from P4 spec, where you do symbolic configuration.
Yes.
Using that, you build a branch, so then you do that.
Yes, that is correct. And the place where we use P4 simulation, not symbolic execution, is to figure out the expected output packet. So that would be the middle part here on the slide. I think I got roughly the question was about hashing. How do we know what's the expected behavior for hashing? So we simplify things a little bit there. We cheat a little bit. Basically, instead of saying, oh, this is exactly how we expect the switch to hash packets, we basically compute, in the simulator, we allow any of the possible outputs. And then we only test that the switch does one of the legal things. Yeah, one more question.
Yeah, back with Open vSwitch, there's for their OpenFlow implementation, which I'm sure you guys are very familiar with.
Yes.
There's a utility in there. You can't quote it, but it's basically an OF proto trace function where you can say, given this packet with these header characteristics, what will the switchboard plan do with this? So that's really handy in OpenFlow for debugging how a packet would be treated on the switch. Have you found something equivalent to that for P4?
OK, the question was, Open vSwitch had some functionality where you could get a packet trace showing all the different table entries that were hit for a given input packet. Is there an equivalent in P4? Yes, indeed. And this is super handy in debugging or explaining why we expect a certain behavior. The P4 simulator called BeamV2 does give you such a trace. It's given as a log, which is not ideal. We actually have a project underway where we return that trace in a more machine-readable way, as a more structured output. And yeah.
Do you know if that's a specific to the BeamV2 platform, like with Nix or something else like that, have its own tool?
So BeamV2 is a pretty generic tool, meaning well, I have to be a bit careful there. So BeamV2, you can run any P4 program on BeamV2. For Nix, you probably need a different architecture than what we currently use, and that would need specific support in BeamV2. It's written in a sort of extensible way, so that could be added. And in fact, there are some people working on a P4 architecture called PNA, the portable NIC architecture. And yeah, so that isn't yet supported in BeamV2, but could be pretty easily added. It's sort of a framework that can support different architectures. Yeah?
So if you use the same P4 spec for both simulator as well as for the physical switch, how do you find out in this scenario, how do you find out any bug in your P4 spec?
Yeah, that's a great question. So basically, when we notice there's a difference between the real switch and the spec, we report a bug. And yes, one possible outcome is that the bug is not in the switch, but in the spec. And that would generally, sorry, let me jump here. that would generally come out during the root causing process, right? The engineers, the switch engineers might say like, well, that's actually expected behavior. Your bug report is wrong. And so then we go back and we update our specification.
You will not even go into the root cause analysis because of the bug, both your expected and actual.
So you're saying what do we do if the exact same bug is present in the switch and the specification? Then we wouldn't find it, right? So that is correct. However, the way we think about, so we think this is very unlikely, and here's the reason why. Like having a bug is a pretty low probability event, and the people who implement the switch and the people who write the P4 spec are different people. So we think of these as independent probabilistic events. And then math tells us that if you want two independent probabilistic events to happen, the probability of that happening is the product of the two probabilities. So if both of them are low probability, together they're really low probability. So yes, in principle, absolutely this can happen, but it's not a huge concern in practice. That doesn't mean this would never happen, absolutely.
But I think you probably need some other way to validate your P4 spec. At least, I don't know if you have some other means of actually validating it. So if you are defining the pipeline, in a sense, that doesn't have any issues.
I mean, so the other way so the comment was we probably need some other way of validating our P4 pipeline. I mean, the way that is obviously validated is through human review, right? So whenever we make changes to the P4 spec, it goes through a normal review process. And then maybe the second way it gets validated is that our SDN controller, when they figure out how to program the switch, I mean, they take the P4 specification and they say, oh, does this match our requirements? Can we implement what we want to implement based on this specification? And if they can't, they come complain to us. But so it's sort of vetted in that way. Any other questions? 3 more minutes. If not, thank you so much.